Our lesson today is on logarithmic functions. This is again a topic that you saw in Algebra 2. So first let's talk about the relationship between a logarithm and its exponential form. So this would be the exponential form of an equation. The corresponding logarithmic form. So we start with the word log, L-O-G. The base of the exponent becomes the base of the logarithm. So since this is base b, this log is going to be base b. And then the exponent is on its own side of the equation. So this is the logarithmic form. So we can go back and forth between these forms as needed. So for our examples here, we're going to evaluate different logarithms. So log base 2 of 16 is a value. If we think about it exponentially, we're saying 2 to what power gives me 16? Well, in this case, 2 to the 4th gives me 16, so log base 2 of 16 is equal to 4. Log base 5 of 1 over 125. So again, we're saying 5 to what power would give me 1 over 125? Well, 5 cubed is 125. So to put it in the denominator, instead of 5 cubed, it's going to be 5 to the negative 3. So log base 5 of 1 over 125 is negative 3. Log base 17 of 17. We're saying 17 to what power gives me 17? Well, obviously that's going to be 1. And finally, log base 2 of negative 8. So 2 to what power would give me negative 8? There is no value that we can raise 2 by to get a negative 8. So there's no answer here. We cannot take logs of negative values. And if you picture the graph of 2 to the x, there is no negative. So there is no power that we could raise 2 by that would give me a negative value. So some very basic properties of logs. The first one is log base b of 1. So we're saying b to what power equals 1. That's always going to be 0 because anything to the 0th power is 1. So log base anything of 1 is going to be 0. Our second one, log base b of b, just like our example log base 17 of 17 is always going to be 1 because if we're taking something raised to a power to get the same thing, that power is always going to be 1. Log base b of b to the x is always going to simplify to be x. So the log base b of b basically cancels itself out, and we'll talk about why later. And then the other way, b raised to the log base b of something is going to be that something. So we're going to do some quick examples. So let's say I have log base 12 of 12 to the x plus 2. The log base 12 of 12 cancels each other out, so this is just x plus 2. Okay, here I've got log, or 10 raised to the log base 10 of sine x. So again, the power of 10 and the log of 10 cancel. So this just leaves me with sine of x. And this is a strategy that we will use when we get to solving equations. There are two common, or let me say, frequently used specific logarithms. There are common logarithms and there are natural logarithms. Common logarithms is a log with a base of 10. So if you have log base 10 of something, the way we will write it is just log of something. We don't have to write the 10. So if there's no value there as the base, then we understand that base to be 10. Natural logarithms are a log with a base of e. So log base e of x, the notation is going to be ln x. So we have natural logarithms and we have common logarithms. So now we're going to talk about some basic properties of ln of x. These are going to be the same, just we're going to use it with a natural log. So natural log of 1, log base anything of 1 is always going to be 0. So natural log of 1 is 0. The natural log of e, so its base e of e, is always going to be 1, which means that natural log of e to something is the something, so natural log of e to the x is x, and then e to the natural log of x is equal to x. And again, these are something that we can use when solving equations. So if I had natural log of e to the x squared, that's going to just simplify to x squared. If I had e to the natural log of 7, this is just going to be 7. So the big deal here is that exponential functions and logarithmic functions are inverses, and we'll illustrate this in a second. But that's the big relationship here, and that's why when you do something like natural log of e to the something, it simplifies down to just whatever that is, because the composition of a function and its inverse always results in x. So let's find the inverse of 2 to the x. Okay, so we know the inverse, we switch the x and the y. So x equals 2 to the y. And we're going to simplify this. We want to solve for y. Well, what we're going to use is we're going to change the form. So remember, y equals b to the x goes to log base b of y equals x. So the exponent comes out. So if I change this form, this is going to be log base 2 of x is equal to y. Okay, so 2 to the x and log base 2 are inverses, and that's going to follow with all of the other bases. So we're going to make a list of different inverses. We're going to have the exponential one here and the logarithmic one here. So y equals b to the x, any base. The inverse is going to be log base b to the x. If the base is 10, then our inverse is our common log. And if our base is e, then our inverse is the natural log of x. So you can write this down if you want, but this is old news. So we're going to be graphing, and the thing that we want to remember is that a function and its inverse are symmetric to the y equals x. So if I want to graph an inverse, I want to switch the x and the y coordinates. Okay, so you should have this sheet where we're going to be graphing different logarithms. So the first one we're going to graph is log base 2. So this is going to be the inverse of y equals 2 to the x. So I'm going to graph 2 to the x because we know what that looks like. Crosses at 0, 1, 1's at 2, 2's at 4. So this is 2 to the x, and I'm going to use that to graph log base 2. So we're going to switch the x and y coordinates. So here I have a point at 0, 1, which means we have a corresponding point at 1, 0. The point 1, 2 is going to be at 2, 1. The point 2, 4 will be at 4, 2. Looking back here, I have a point at -1 at 1/2. So that means at 1/2 we're at -1. So this tail reflected over the line y equals x is going to approach the y-axis now. So this is what log base 2 of x looks like. It has a vertical asymptote at 0. Like we said before, we can't take logs of negative values because there are no negative values on the exponential function. So this next one's just going to be moved to the left 3 and up 4. So what I'm going to do is we're going to take this graph and move it. So I'm going to create a new vertical asymptote at -3. And then we're going to take this graph, slide it back, and then up 4. So the first point that would cross at 0, well, 1 away at 0 is going to be up 4. 1, 2, 3, 4. The next one's going to be 1 over. Like so. Log base 1/2. So what does a 1/2 base look like? So this is going to be the inverse of 1/2 to the x. 1/2 to the x is exponential decay. So that graph looked like this. So we're going to take those points and reflect it over the line y equals x. So y equals x is going to be here. So this thing is going to kind of end up on itself, but I can still go point by point. So 0, 1 is going to be at 1, 0. -1, 2 is going to be at 2, -1. My -2, 4 is going to be at 4 and -2. This point here is at 1, 1/2, which means we're going to have 1 at 1/2 and 1. So this graph is going to look like that. So kind of a weird one, not one that we see a whole lot, but we can always arrive at it by graphing the inverse. A natural log of x, its inverse is e to the x. So we graphed e to the x already. So e, really we have the two main points. So 0 is at 1 and 1 is at 2.718. And then we just know it's exponential growth. So for natural log, the two corresponding points, the 0, 1 is going to be at 1, 0. The 1 e is going to be at e, 1. So going over about 2.7 and then up 1. And then we'll graph like that. This one's going to be moved left 2. So I'll just create a new vertical asymptote at -2. And graph my 2 points. This one's going to be moved up 2. So we're just going to take the point that would be at 1, 0. It's going to be up at 2. The point that would be at E, 1 is going to be at e up here at 3. Down here, this one, we're going to talk about properties of logs in a second, but if you remember from last year, if we have something to a power, or log of something to a power, we can bring that power out front by multiplying. So this is going to be the same as natural log 3 natural log of x minus 2. So this is going to be stretched vertically by a factor of 3 and moved to the right 2. So I'm going to do a vertical asymptote at positive 2. The 0 one is going to stay there, but the E1 is now going to be at E3. So that graph's going to look like that. This one's going to be moved down to stretched by stretched vertically by 2. So the 0's just going to, well, it would be this point here is going to be moved down to. The next point would be at E1. It's going to get brought down by 2, but then multiplied by 2. So it's going to end up at a positive 1 there. And then natural log of e to the x is just y equals x. Like so. The last thing we're going to talk about are the properties of logarithms. We talked about the basic properties, but these are the more advanced ones. So the first one is the product property. Okay, where if I have log base b of a product, m times n, I can split that up to log base b of m plus log base b of n. So if we have a product, it can be split up using addition. Quotient's going to follow that. So if we have log base b of m over n, we're going to split that up with subtraction. So log base b of m over n is going to equal log base b of m minus log base b of n. A power, so if I have log base b of m raised to the nth power, the n's going to come out front and become the product. So it's going to be n times the log base b of m. And this is a really, really convenient or functional rule. So we're going to be using the power rule a lot to deal with exponential functions. If we want to get the n from being an exponent, we can use logarithms to do that. The last property we're going to have is the change of base property. So the change of base rule, if I have log base b of m, I can rewrite this introducing a new base. So I'm going to write this as log. We're going to come up with a brand new number, or letter in this case, c, of m over log c of our base. So the top stays on, so this is top, call that bottom. So this is on the top, this is on the bottom, and then we introduce a new base. Where this is helpful is if we change the base to either base 10 or base e, because that is what is on our calculator. So now we're going to use the rules to evaluate. So we're going to evaluate, which means I want a value, log base 2 of the cubic root of 32. So first thing we're going to do is rewrite this as log base 2 of 32. Rather than the cubic root, we'll raise it to a rational exponent. Now I can bring that up front. So 1/3 log base 2 of 32. So log base 2 of 32, 2 to what power is 32? That's going to be 5. So we're going to have 1/3 times 5, or 5/3. Our next one, 3 natural log of e to the 4 minus 2 natural log of e squared. Natural log of e to the 4 is just going to be 4. Natural log of e squared is just going to be 2. So we're going to have 12 minus 4, which is 8. Last one, log base 4 of 3.7. So 4 to what power equals 3.7? Well, we don't know that. But what I can do is rewrite this using the change of base. So on the calculator, we have log and we have natural log. So I can rewrite this as log 3.7 over log 4, or we can use natural log, and then I can use that. So if you look, we have two buttons, the log and the natural log. So we're going to do log 3.7 divided by log of 4, and that gives me 0.943. And it makes sense. 4 to some power equals a number less than it, that it'd be less than 1. Now we're going to use the properties of logarithms to expand some big thing here. So we have the natural log of x plus 1 to the 4th, the square root of 3x minus 4, all over sine squared x. So the first property I'm going to use is the quotient rule, which says if I've got the natural log or log of a quotient, it's going to be the natural log of the top minus the natural log of the bottom. So we're going to have natural log of x plus 1 to the 4th. I'm going to rewrite this as 3x minus 4 to the 1/2 minus natural log of the bottom, which is going to be sine of x squared. If you have sine and the squareds in the inside, it's really sine of x squared. Now I'm going to use the product rule to break these up. And then the last rule I'm going to use is the power rule on all three of these. So this is now going to be 4 natural log x plus 1 plus 1/2 natural log 3x minus 4 minus 2 natural log sine x. And that is considered expanded. For our next example, we're going to basically go backwards. So we've got 1/2 log base 4 of x minus 3 log base 4 of x minus 2. So going in reverse order, first rule I'm going to use is the power rule. So this is going to be log 4x to the 1/2 minus log 4x minus 2 cubed. Now I can use the quotient. So this is going to be log 4, the top, x to the 1/2, or you can write it as the square root if you want, over x minus 2 cubed. So that is logarithmic functions. We will be using that to solve equations over the next couple of lessons.